So we are here ready to discuss equivalent couples, and we saw in the previous video at the end we mentioned that there exists another couple floating in space, another two forces that create the same moment, and then those couples are said to be equivalent, if they cause the same moment. So friendly reminder, Friendly reminder, vector multiplication, A cross B, finger goes with A, the middle finger goes with B, A cross B given by the thumb, perpendicular to both vectors. So we need this because we'll be after this point we'll have to be really comfortable determining the sense of our moment vectors. So equivalent couple, equivalent couple. Two couples are said to be equivalent, Two couples are said to be equivalent if they produce the same moment. If they produce the same moment. So let's take a look at this box, Let's take a look at this box. It has some forces acting on that box, and the forces appear to be couple related, For example, these guys here, they seem to be a couple, and these guys over there, in the top, they appear to be a couple too because they are identical in the opposite sense. For instance, what is the distance between these two guys over here? Well, if we choose a position vector oriented that way, we have to use this force, This force to calculate moment about that, So we find that the moment in this case, creates a rotational tendency going this way, and I have determined the sense of the rotation just by looking at the forces, just by inspection, By inspection, when these forces act, This force coming this way, this force coming this way, they create this kind of rotational tendency, It's 2 times 100, 2 times, this is 1 meter separation. So is 1 meter times 100 gives me 100 Newton meter, So this guy is 1 meter here. And then the resulting moment is 100 Newton meter oriented upward, Oriented upward. What about these two guys, What about these two guys? This guy and this guy. So if we orient a position vector like that, That position vector is 2 meters, 2 meters. So the moment is going to be 2 times 50, 100. The rotational tendency, just by inspection, I can determine it to be like that. So it's 100 going upward, The same moment as the other couple, And then it's 100 Newton meter, Same value as the other. So the set of forces we have in this drawing, they are equivalent couples because they produce the same moment, On the previous diagram, there were two equivalent couples, The forces were different, and the moment arms between these forces they were different as well, but the rotational tendency was the same, So we did these calculations, And then even though the perpendicular distances were different, the forces were different, we got the same rotational tendency, So something that appears quite often in rigid bodies, Now, we know now that we can move couples to any point in a body because they would create the same moment, For example, I have a body. Let me just describe a body for you. So this body has some supports, Some supports, the same supports that we were discussing the other day, Some supports. It's a rigid body supported onto many things. And then there is one couple of forces over here, Well, we can move that couple at a different location, and we will preserve the rotational tendency, or will keep the same rotational tendency on the body, Because the position of the couple doesn't matter, It's just force times distance, and that is what gives the the total moment, right? So if several couples act on a body, right? If several couples act on a body, the individual couple moments, right? The individual couple moments can be moved to any common point on the body, right? Move to any common point on the body and added together to get the resultant moment couple, right? So we move them all together and we add them, right? The couples acting on a body, and we get the resultant couple moment or the resultant moment couple, right? So we can add them, right? So for example, these guys, right? This rigid body has two couples acting on it, right? We obtain the rotational tendency of them, right? We add it together. Careful with the signs because they may actually have different rotational tendencies of going into the opposite sense. We add them together and we represent the total moment in this body with a single moment, right? With a single moment, which is the resultant moment couple. So for example here, right, there is a body subjected to two couples, and you can see that the two couples act, or they are placed on different locations of the rigid body, right? So we are asked to find the resultant moment, MR. Well, one strategy would be to calculate the moment caused by one couple, right? Let's say the red couple, and then calculate the moment caused by the blue couple, and then we add those together, right? And then we will obtain the total moment caused by these two couples on that body, right? Here we are not even expecting that the moment caused by the red forces is equal to the moment caused by the blue forces, right? We are talking about adding the moments coming from the couples, right? They don't need to be the same, right? We are going to add them anyway, right? We are going to add them anyway. So let's do it, right? So I have here the in terms of an equation, right? That the resulting moment has to be the same as or equal to the moment caused or in the first couple plus the moment from the second couple, right? From the second couple. So in these two couples, right, I have gone ahead and decided which R I'm going to use. Remember, depending on the R you're going to use is the force you want to cross, right? So for example, this is the opposition vector here, and then this is the force vector I have to use, right? The force vector you need to use depends on how you defined that position vector. So for the red couple, right? For the red couple, I have that my position vector is just minus j hat, right? You can see that my vector goes to the negative sign of y, so it goes with minus j hat, and it has a magnitude of 2, so the position vector is minus 2 j hat, right? Minus 2 j hat, right? And then we have to cross with the force F1, right? With the force F1, which right, with which is equal to 50 newtons in the positive sense of x, so it is 50 times I hat, right? 50 times I hat. So it is minus 2 times j hat, and the force is 50 times j hat. That is our first moment. What about the blue couple, right? So my position vector goes down on z, and then goes down by 1 meter, because this guy is 1 meter. Let me use blue, right? This distance is 1 meter, so this guy is 1 meter going downward, so it's minus 1 k hat. And what about the force vector? Well, the force vector is 60 j hat, because the force is 60 and goes to the positive side, for the positive side, so it's 60 j hat. So now I have to cross them. All I have to do is cross them and add them together, right? So this is the operation, right? Minus 2 j hat cross 50 I hat, so it's these two guys, right? Plus, right, minus 1 k hat cross 60 j hat, right? And that is equal to the resultant moment, right? Watch for the signs, right? Remember to keep the signs. So, okay, this is the cross product for the one moment, right? And this is the cross product for the other one. So once you do the math, right, you get 100k hat plus 60 I hat. So the resulting moment is 60 I hat plus 100k hat kilonewton meter. So what did we just do? We saw that a rigid body was acted by two couples, right? And we calculated the total moment that rigid body was experiencing, right? What if that body would have had acted not by couples but by forces? So let me just go back a few more slides. So what if the rigid body, right? I'm just going to would have been acted by different forces. So for example, a red force coming this way, right? And a green force coming this way, right? And then if you are asked to calculate the total moment, well, it's the same thing. You first take care of the couple moments, right? In just the way that we did. And then we calculate the moment caused by this green force, right? About whatever point you were told, right? And then the moment caused by this green force about the point that you were specified, right? But nothing strange, right? We can calculate total moments if the rigid body is acted by couples or single forces. For the single forces, you need to be given a specific point, right? It matters which point do you want to calculate moments about. If you have couples, you know that it doesn't matter which point do you get, right? The moment will be the same, right? So that's what we just did, right? Calculated total moments in a rigid body, and those moments were produced by couples. But we could as well have single forces causing moments, right? So now we have one typical problem, right? Let's increase the interest level. So this is very interesting. Remember, right? Don't feel scared by figures, right? Read through the problem, right? It's just many times it's just geometry, right? It's just a trigonometric problem, but the concept should be really easy, right? So let's see what happens. So this problem has two parts, part A and part B. Let's see what the problem says. If the force is shown, right? So first of all, right, let's take a look. Well, this appears to be a pipe, right? A pipe. It's probably there in the sink, right, or in the basement of your house. It's a pipe, and the plumber, right, or yourselves, right, you are applying some moments with these wrenches, right? These wrenches coming up, and these wrenches coming down, right? So you are trying to twist that pipe. Why do you need to twist that pipe? Who knows, right? Hopefully, it's something safe, because otherwise you're going to fill your basement with what I would hope is clean water at least, but it's going to get flooded. So anyway, so you are applying two moments there. And then, well, it just so happens that the force is the same. Well, this force coming up is 100k hat newtons, and then this force coming down is also 100k hat. Well, this minus 100k hat. Find the couple moment. It says, find the couple moment that acts on the assembly, right? By this point, we are not surprised they are not giving us a point, because it doesn't matter, right? The moment caused by a couple doesn't depend on the point or in any point, right? It will be the same. So careful, right? Don't worry because they don't give you a point, right? It's a couple, so it should create the same moment everywhere. Express the result as a Cartesian vector, right? Be careful. Remember, VA member BA, so member BA lies flat on the XY plane. Here is my XY plane. Right, so this guy over here. Okay, the couple moment. Well, shall we read part B? Okay, let's read part B, just to be scared completely, right? Before we go into solving this problem. Well, you know what? No, we won't read part B, right? We'll just do one, right? The part A, and then we'll worry about part B later. Sounds good? Okay. So they are giving us the information about the forces, right? It's clearly a couple. It has the same force, right? One of these forces is the same as the other, so it's clearly a couple. And they are asking us to find the couple moment, right? Okay, if you remember, right, all we have to do is to shoot a position vector from one vector to the other, and that's it, right? And that's all we need to do. And then we cross that position vector with the force that we just hit, right? And that is what they are asking us here, right? So let's see. So we can define, right? We forget about part B, right? And this is one possible solution, right? This is one possible solution. They defined a position vector that goes from this point to this point, right? That is my position vector. And then we have to cross it with this force, right? With this force. You know what? I'm going to use green color so we can follow the colors. So we shoot a position vector from this point to this point, and we cross it with this force. That is what part A wants, right? So in order to do that, we have to find the coordinates, the coordinates of D, and we have to find the coordinates of C, right? That's all we need to do, because then we can find the position vector RDC, right? Let's see. The moment is R cross F, right? R cross F. Don't look at that. R cross F, and that's all what they are asking us to do, right? Well, I'm not going to lie to you. Right? I'm not going to lie to you. But this problem is actually quite trigonometry intensive, right? So this is my solution, right? That's my solution, and I think I did my kid on the dinner table one day, right? It was about 11 p.m. or something, and it took me a while. It took me a while. It took me an embarrassingly large amount of hours, right, into the night to get all the trigonometry correct. If you take a look at it, this is the plan view of axis X and Y, as you see, X and Y axis right here, and this is your coordinate or your point D, and this is your coordinate or your point C, right? And this is all the triangles and all the calculations needed to find the coordinates, right? Which are, let me just remove this, here and here, right? So I try to kind of do the calculations in order. So if you do the blue calculations first, and then the green ones, and then the red ones, and then you should arrive to the final projections in kind of that golden orange color, you should be fine, right? But the bottom line is that one way or the other, you have to find the coordinates of C and the coordinates of D. The problem is just R cross F, right? And this is just thrown in there just for fun, right? So you shouldn't feel discouraged, right? Discouraged. If you can get that, is that the whole problem is R cross F, that's fine, right? That's all I want you to do, realize at this point. So here are my coordinates, and then knowing C and D, I can find my position vector RDC, right? C minus D, coordinates of C minus the coordinates of D, and I find my position vector D to C, right? The next step is to cross it. Right, with the force vector. Not this one, but this one, right? Because the position vector goes from this point to this point. So that vector is 100 k hat newtons, right? And then I have to cross it. So I do the cross product, and I obtain, right? I obtain that the moment is 7 I hat plus 42.1 j hat Newton meter. That is what we get asked in part A of the problem. And then there is no magic here, right? It was very tedious, but we got those coordinates down, right? And now we can focus on part B, right? Take a look. Part A, this was our moment, right? And then, somebody went ahead and calculated the magnitude, right? Just the square root of the square of the two components. So these two guys square, and then somebody did the square root. And they found that the magnitude of that moment is 42.69, right? So that's good. And why is that interesting? Because let's see what part B has to say. If the magnitude of the resultant couple moment is 15, okay, wait a minute. What did I get as a magnitude in the previous part? Well, we got that it was 42.69. Well, if the magnitude is supposed to be 15, find the magnitude of the force, right, applied to the ranges, right? Well, at this point we have to work backwards. We know the magnitude, and we have to know what sort of force I have to have both here and here. Remember, they are a couple, so they have to be the same in order to have a magnitude of 15. So there are a number of ways to do it, right? You can even, for example, if that was 42, right, it's just a proportion, and then you could try lowering this number, right? Lowering this number until you get the magnitude as 15 in a trial and error process. You know what? Don't feel strange if you prefer the iteration way. It can be you can propose an equation and solve the equation, right, directly, one step, or you can try an error. You can use try and error, and then right. That's a very engineering way of thinking, right? Try and error is a very engineering way of thinking, right? You should feel really proud if you want to go through that route, right? Or we can propose an equation, right? Advantages of try and error is that if you made a mistake, you can fix it in the next iteration. And if you make a mistake setting up an equation, right, you can never recover, right? Because you won't know, unless you check, you won't know if there is a mistake, right? So here is my position vector. That is not going to change, right? The 2 points, we are told that, we didn't get told that they are going to change. So position vector is the same. RDC is equal to that, right? But the force, right, is some magnitude times k hat, right? And the magnitude of the moment has to be equal to 15, right? So those are the conditions of the problem. So I can work backwards, for example, here, and I can maintain my force, right, and leave it as a variable on my cross product. So once I do my products, right, 0, 0, some value, right, j hat, and then some value I hat, 0, 0, I find that my moment, right, is equal to this, right? Take a look. That is the moment caused by this force. I know that the magnitude, right? I know that the magnitude has to be 15, right? So the next step is to find the magnitude. Here there was a transformation of units, right, from millimeters to meters. So everything got divided by 1,000, right? And then the next step is to find the magnitude, make it equal to 15, and leave one variable inside, right? Which can be solved using your calculator. And then F is equal to 35.1 newtons, right? So that takes care of part 2. Moral of the story: don't feel scared of leaving variables inside your cross product, right? It's the key to many times to solve problems, right? So don't feel afraid, right? If you want to put just numbers in there, know that you can carry variables inside the cross product, inside the determinant. Nothing wrong with that. Nothing wrong with that. So we have reached the next topic, which is reduction of force systems to a force and a couple, and then that's what we are going to do in the next exercise. Sometimes we have rigid bodies acted by many forces and couples, right? And we can add what we can add, right? And then just leave a system that has only one force and only one couple. So we'll explore that case in the next video. See you on the other side.